A perfect opposite of our universe could be real. The mirror universe hypothesis proposes a cosmos where time runs backward and matter is replaced by antimatter, a scientific idea that reshapes reality itself. By the end of this, you will understand how this theory could solve the biggest mysteries of the cosmos. We will explore if a mirrored reality leaves traces in the darkness of space, and what it means if our existence is balanced by an inverse twin. How would your perception of reality change if nothing was truly unique? A reflection in a pond captures light, but what if it could capture an entire cosmos? The mirror universe hypothesis suggests exactly that, a parallel reality where every physical property is fundamentally flipped. Positive electrical charges become negative. Left-handed particles, a fundamental property in particle physics, become right-handed, and the very flow of time itself could potentially run in reverse, like a film played backward. This concept is deeply rooted in the symmetries that physicists use to describe our own universe. One of the most important is called CP symmetry, which stands for charge and parity. It is the idea that if you swapped every particle with its antiparticle and viewed the universe in a mirror, the laws of physics should remain the same. Yet experiments show they do not. This violation of CP symmetry reveals a fundamental imbalance, a preference for matter in our cosmos. This very flaw is what makes the mirror universe idea so compelling to scientists. It was figures like the physicist Andrei Sakharov who explored how such an asymmetry in the early universe could mean our matter-dominated existence is balanced by an antimatter-dominated twin. This is not the sprawling multiverse of infinite possibilities you might have heard about. A mirror universe is a specific, precise opposite, a cosmic inversion of our own reality. So if this perfect twin does exist, how could we ever hope to find it? The search for an answer leads us into some of the most profound experiments ever conceived. The universe, it turns out, has a distinct left-handed preference. This startling discovery emerged not from grand cosmic observations, but from the delicate, invisible dance of subatomic particles. In the 1950s, scientists were baffled by a particle called the tau-theta puzzle. Two particles, the tau and the theta, appeared identical in every way: mass, lifetime, everything except for one bizarre detail. They decayed in ways that suggested opposite mirror-handedness or parity. How could two seemingly identical entities break the fundamental rule of mirror symmetry? This was the crack in the door. Two brilliant physicists, Tsung-Dao Lee and Chen-Ning Yong, dared to propose the unthinkable. They suggested that perhaps this mirror symmetry, this parity, was not a sacred law of the universe at all. It was a hypothesis so radical that when they won the Nobel Prize for its subsequent confirmation, the scientific world was set ablaze. The weak nuclear force, the very force responsible for certain types of radioactive decay, was found to be left-handed. It fundamentally distinguishes between left and right. Our universe, on its most basic level, is not symmetrical. This violation of parity was a profound shock. It meant the cosmos had a built-in preference, a direction, and with that realization, a tantalizing question was born. If our universe leans to the left, could there be another, identical in every way, that leans to the right to balance the cosmic scales? This was not merely about particles. The human mind has always been drawn to the concept of the double. Long before particle accelerators, myths and stories spoke of mirror worlds and shadow realms. Even the discovery of mirror neurons in our own brains, cells that fire both when we act and when we see another act, provided a powerful biological analogy for a universe that reflects our own. The scientific speculation grew from a curious puzzle into a formal hypothesis. What if mirror particles and even a mirror cosmos existed, hidden from our view, interacting with us only through gravity? This elegant idea promised to restore a deeper, hidden symmetry to reality, transforming a philosophical curiosity into a tangible, if elusive, scientific target. The stage was now set for a hunt unlike any other. This missing antimatter is one of the greatest puzzles in all of science. We know that for every particle of matter created in the Big Bang, an equal particle of antimatter should have been born. They are perfect opposites, identical in mass but with reversed electrical charges. An electron with its negative charge is mirrored by a positron, its positive antimatter twin. When these two meet, they do not simply cancel each other out like numbers on a page. They vanish in a flash of pure energy, a process known as annihilation. If the universe began with perfect balance, all of this matter and antimatter should have annihilated one another, leaving behind a cosmos filled with nothing but fading light. Yet here we are, in a universe made of stars, planets, and people, all built from the matter that somehow survived. So where did all the antimatter go? This is the Barrian asymmetry problem, a gap in our understanding so profound it threatens to rewrite the story of creation itself. One elegant solution proposes that the antimatter did not simply vanish. It is all still here, but residing in a perfect mirror copy of our own reality. In that parallel cosmos, anti-stars shine in anti-galaxies, built from atoms where positrons orbit anti-protons. The two universes, matter and antimatter, were born together but were somehow wrenched apart at the very beginning, forever separated by a fundamental barrier to prevent total annihilation. This is not just a wild speculation. Scientists are testing the very foundations of this idea in the most advanced laboratories on Earth. At CERN, the European Organization for Nuclear Research, physicists create and trap individual atoms of antimatter, holding them in magnetic bottles away from any contact with normal matter. They are studying its properties with incredible precision, asking a simple but revolutionary question: does antimatter fall down, or could it possibly fall up? If antimatter were to defy our expectations and be repelled by gravity, it would be a monumental discovery. It would suggest that antimatter genuinely belongs to a different set of rules, a different gravitational landscape, perhaps even a mirror realm that pushes where we pull. Every experiment that confines a wisp of anti-hydrogen is a direct test of this mirror cosmology. The search for this missing half of reality forces us to look deeper into the nature of existence itself. If a mirror antimatter universe does exist, gravitationally entwined with our own but otherwise invisible, how would its presence make itself known in the darkness of our night sky? The elegant dance of CP symmetry is a cornerstone of physics, a principle that insists the universe should not care about left or right, or matter versus antimatter. It combines two perfect inversions: charge conjugation, which swaps every particle for its antiparticle, and parity, which mirrors everything as if in a looking glass. In a truly symmetrical cosmos, these twin reflections would be indistinguishable from the original. The universe would be perfectly ambidextrous, yet it is not. In the 1960s, a stunning discovery shattered this ideal. Physicists James Cronin and Val Fitch, studying the decay of elusive particles called neutral kaons, found a tiny but undeniable crack in the mirror. These particles decayed in a way that betrayed a fundamental bias. The universe, it seemed, had a slight but crucial preference for one-handedness over the other, violating the sacred rule of CP symmetry. This was not a minor observation. It was a revolution that earned them the Nobel Prize and provided the first tangible clue to the ancient mystery of our own existence. Why is there something instead of nothing? This CP violation is a necessary ingredient for the survival of matter, a fundamental lopsidedness in the laws of physics that allowed a tiny excess of matter to survive the primordial annihilation. Without it, we would not be here, but this very asymmetry raises a profound new question. If our universe is lopsided, where does that imbalance go? The mirror universe hypothesis offers a breathtakingly elegant answer. Perhaps the violation of CP symmetry we observe is not the final word, but merely our local perspective. In a perfect mirror cosmos, the rules are flipped. Its version of CP symmetry would also be broken, but in the exact opposite way. Where our universe prefers one-handedness, the mirror universe prefers the other. Think of it as a cosmic set of scales. Our side of the universe appears heavy with matter, but that weight is perfectly counterbalanced by the antimatter dominance of our hidden twin. Our local imbalance is merely one half of a perfect global symmetry. The flaw we discovered in our own reality is not a flaw at all, but a fingerprint, a whisper of a vast and hidden reflection. This idea transforms a puzzling asymmetry into a profound new symmetry, a harmony played out across two parallel stages of reality. So if our universe and its mirror are two sides of the same cosmic coin, forever linked by this elegant balance, what force could possibly keep them from touching and destroying each other in a blaze of mutual annihilation? A perfect opposite cosmos demands more than just swapping left for right or matter for antimatter. It requires a fundamental inversion of every single physical property, a complete rewriting of the cosmic rulebook. Think of it as turning reality inside out. In such a universe, the very constants that govern reality could be different. The fine structure constant, a number that dictates the strength of electromagnetic interactions, might have an inverted value. Gravity, the force that pulls us together, could instead be a force of repulsion, pushing matter apart, and the flow of time itself would not be the steady march toward disorder we experience. There, entropy would decrease. Chaos would spontaneously resolve into order, like a shattered vase reassembling itself from scattered dust. This is not a simple mirror, it is a cosmic negative. To grasp this, physicists turn to a profound idea known as CPT symmetry. This is the ultimate test of symmetry in our universe. It states that if you simultaneously reverse charge, swap parity, and run time backward, the fundamental laws of physics must remain unchanged. Our universe obeys this rule, but what if the mirror universe is not just a concept, but the actual physical manifestation of this CPT transformation applied to our entire cosmos? In that scenario, our universe and its twin are two halves of a single, perfectly symmetric reality. The lopsidedness we observe, the matter-dominated existence, is simply our local view of a much larger, balanced whole. This raises a deeply puzzling question. What would life be like in such a place? Could there be sentient beings composed of antimatter, whose consciousness flows from their future into their past? They would remember tomorrow and anticipate yesterday, experiencing cause and effect in an order that is utterly incomprehensible to us. Such a thought experiment stretches the fabric of our imagination to its absolute limit, forcing us to confront the very nature of existence. It challenges us to ask if our perception of reality is just one possible configuration, one single thread in a much grander tapestry. If this perfect mirror does exist, how could two such inverted realities ever coexist without instantly canceling each other out? The answer may lie in the one fundamental force that could still reach across the divide. Gravity could be the only bridge between our world and its perfect opposite. This single force, so weak on the human scale yet dominant across the cosmos, might be the sole thread connecting two mirrored realities. To understand how this is possible, we must look at the mathematical blueprints that physicists used to draft these cosmic twins. The equations of string theory, for instance, suggest our entire universe could be a three-dimensional membrane or a brane floating in a higher dimensional space. Right next to ours, separated by a gap smaller than an atom, could be another brane, a perfect mirror of our own. On that parallel sheet of reality, every star and galaxy would be made of mirror matter, particles that have their own forces and interactions, completely invisible to our light. They would be ghosts in the cosmic machine, felt only through their gravitational pull. This is not just a fanciful idea. Experts like Lisa Randall have worked with models where such a warped geometry could naturally explain the profound mystery of dark matter. The immense, unseen mass that holds galaxies together could simply be the gravitational weight of the mirror universe pressing against our own. One detailed framework is the mirror matter theory, developed by scientists like Robert Foote. It proposes a complete duplicate sector of particles, a shadow copy with its own version of photons, electrons, and quarks. These mirror particles would not interact with our electromagnetic force, which is why light passes right through them, but they would tug on us with gravity. Another model ties the mirror cosmos directly to the antimatter problem, suggesting that a period of hyper-fast expansion in the early universe, known as inflation, physically wrenched the matter and antimatter realms apart, placing them in separate domains. Each of these theoretical frameworks comes with its own set of predictions. They suggest we might find clues in the subtle behavior of neutrinos, those elusive particles that flicker between different types as they travel. A mirror universe could cause anomalies in this oscillation, a faint fingerprint in the data. Others propose that the gravitational waves, the ripples in space-time from colossal cosmic events, might carry an echo if they ever washed against the shores of the mirror realm. These mathematical models are more than abstract puzzles. They are the essential tools that transform a captivating story into a testable scientific quest. They give us a map pointing our telescopes and detectors toward specific signs in the void. The search for this cosmic reflection is no longer just a question of philosophy. It is a hunt for evidence, guided by the precise lines of equations that describe a hidden reality. The night sky holds more than just stars. It might conceal the faint outlines of another reality entirely. Astronomers are not just looking at the light, they are searching for the shadows that a mirror universe would cast upon our own. One of the most tantalizing places to look is the cosmic microwave background, the ancient afterglow of the Big Bang. This faint radiation is a baby picture of the cosmos, and it should be almost perfectly uniform. Yet, scientists have found strange anomalies, like a mysterious alignment nicknamed the axis of evil. This unexpected pattern in the temperature fluctuations defies standard predictions, leading some to wonder if it is a cosmic bruise, an imprint left from a collision with our mirror twin in the primordial chaos before inflation stretched space-time. It is a faint echo, a possible whisper from the other side. Gravity provides another set of clues. We see galaxies spinning so fast they should tear themselves apart, held together only by the immense gravitational pull of unseen dark matter. But what if that dark matter is simply the ordinary matter of the mirror universe, forever hidden from our sight but forever tugging on our stars? Observations of gravitational lensing, where the gravity of a massive object bends light from behind it like a lens, sometimes show effects that are difficult to explain with visible matter alone. Could these be the gravitational footprints of mirror galaxies, warping the fabric of our space-time from their hidden dimension? Some scientists even hunt for mirror planets through microlensing events, brief brightenings of a star that occur when an invisible object passes in front of it, its gravity focusing the starlight. A mirror world made of matter we cannot see could create exactly such a flash in the darkness. The evidence is not confined to the vastness of space. It reaches back to the very first moments of creation. The process of Big Bang nucleosynthesis, which forged the first light elements, is exquisitely sensitive to the number of particle types present in the early universe. The presence of mirror neutrinos, sterile particles that barely interact with our world, could have subtly altered the amounts of hydrogen and helium we see today, leaving a fingerprint in the primordial recipe. And what of the stars in that other realm? A mirror star composed of mirror atoms would burn through nuclear fusion just like our sun, but it would emit mirror photons, a form of dark light completely invisible to our most powerful telescopes. It would be a dark sun, detectable only by the faintest gravitational wobble it imposes on the visible stars around it. While no single observation confirms the mirror universe, this growing collection of cosmic curiosities forms a compelling trail of breadcrumbs. Each anomalous lensing event, each puzzling particle decay, and each strange alignment in the ancient light keeps the hypothesis burning bright, a testament to the human drive to find our reflection in the cosmos. Dark matter could be the ghostly silhouette of an entire parallel cosmos. For decades, its presence has been inferred only by the way its immense gravity bends light and holds galaxies together, a substance that refuses to interact with light or matter in any way we can directly see. This is precisely what makes the mirror-universe connection so compelling. What if dark matter is not an exotic, unknown particle, but simply the ordinary matter of a mirror reality, made of mirror protons, neutrons, and electrons? In that other cosmos, these particles form mirror atoms, which coalesce into mirror stars and mirror planets. They have their own mirror chemistry and mirror light, all completely invisible to our eyes and our telescopes. The only connection between our two worlds is the universal force of gravity, a bridge that allows the mass of their stars to pull on our galaxies and our mass to pull on theirs. This elegantly explains dark matter's most puzzling property, its apparent collisionless nature. Mirror matter does not bump into our matter because it is part of a separate cosmic sector, governed by its own set of mirror forces. It simply passes through us like a ghost, its gravitational pull the only evidence of its existence. This also accounts for the way dark matter forms vast, diffuse halos around galaxies. In the mirror universe, its own galaxies would form in similar ways, their halos being the very dark matter halos we observe from our side. The two realities are like overlapping shadows on a wall, each unaware of the other's light, but forever bound by their shared influence on the fabric of space. This idea is more than a thought experiment. Physicists like Zurab Beregiani have explored a fascinating consequence. A neutron star, the incredibly dense remnant of a supernova, could have such a strong gravitational pull that it might actually capture and accumulate mirror matter from its surroundings. As these mirror particles rain down onto the neutron star and annihilate with their mirror antimatter counterparts, they would release a burst of energy, heating the star's surface to temperatures we could potentially detect. We could be looking for the thermal fingerprints of a mirror cosmos on some of the strangest objects in our own night sky. This connection transforms one of cosmology's greatest mysteries into a potential gateway. Dark matter is no longer just a missing ingredient. It could be the tangible gravitational evidence of a complete, functioning universe existing alongside our own, a perfect inversion hidden in plain sight. But how could two such complete and separate realities have ever come to be in the first place? The violent birth of our cosmos might have been a twin delivery. In the first fleeting moments, the universe underwent a period of unimaginably rapid growth known as inflation. a stretch of space-time so fast it could have ripped a single reality into two. Think of a soap bubble expanding, its shimmering surface splitting into separate, non-overlapping domains. Each of these cosmic bubbles could have stabilized with its own unique set of physical rules. One became our familiar matter-filled universe, the other a perfect mirror. During this inflationary epoch, tiny quantum fluctuations, the jitters of empty space itself, were stretched to cosmic proportions. These ripples became the seeds for all the galaxies we see today, but they could have also seeded an entire parallel structure. The mechanism of CPT symmetry, the ultimate rule of reversal, might have been baked into this process from the very start, ensuring that one bubble emerged as the precise inversion of the other. This is not the chaotic multiverse of infinite randomness, but a more structured genesis. In models of eternal or chaotic inflation, our entire observable universe is just one bubble in a vast foam of such domains. Right next to ours, separated by an impassable barrier of inflated space, could be its mirror twin. How exactly would such a perfect opposition form? The key could lie in the field that drove inflation itself, the inflaton. If this fundamental energy field had a mirror partner, a shadow field linked to it by symmetry, then the end of inflation would have played out differently in each realm. As the inflaton fields decayed and released their pent-up energy in a process called reheating, this could have been lopsided. Our bubble might have reheated predominantly into matter, while the mirror bubble reheated into antimatter. This single event could explain the primordial Barrean asymmetry, the great matter-antimatter divorce, not as a random accident but as an inevitable consequence of a mirrored birth. The genesis of a mirror universe transforms the question of our existence from a cosmic fluke into a structured outcome. It suggests our origins are fundamentally dual, that we are one half of a whole. If this is true, then the fabric that separates us from our twin might not be entirely impervious. What faint tremors from that other genesis might still echo in our reality today? An unbreaking egg is not just a magic trick, it's the signature of a universe where time flows in reverse. In our reality, the second law of thermodynamics is the engine of time's arrow, dictating that entropy, the measure of disorder, must always increase. A spilled glass of water never spontaneously refills, and smoke from a fire always disperses into the air. This relentless march toward chaos defines our past and our future. But in a perfect mirror cosmos, this fundamental law would be inverted. There, entropy would naturally decrease over what we perceive as time. Chaos would resolve into order, scattered dust would gather into a statue, and the heat from a star would flow inward, concentrating its energy. This is the ultimate consequence of a universe that is our complete opposite. The equations of physics, for the most part, do not actually forbid this. Time reversal symmetry suggests that the fundamental laws would work just as well if time ran backward. The reason they don't in our experience comes down to a single, monumental puzzle, the initial condition of the universe. Our cosmos began in a state of incredibly low entropy, a highly ordered starting point that set the stage for everything to come. As experts like Sean Carroll suggest, a mirror universe might have had the opposite initial condition, beginning its timeline in a state of what we would call maximum disorder, its Big Bang a state of high entropy. From that moment, it would evolve toward greater order, its arrow of time pointing in the opposite direction from our own. What would consciousness be like for beings in such a realm? They would remember the future and anticipate the past. A decision would be made after its consequences were already felt. Their entire experience of reality would be a continuous process of unfolding causes from effects, a life lived in rewind that would feel perfectly normal to them. This is not a flaw in the hypothesis, but a testament to its profound implications. It forces us to separate the laws of physics from our human perception of them. We are not witnessing the fundamental laws, but rather a single, spectacularly unlikely trajectory through those laws. Observing such a universe directly seems impossible, as any signal we could receive would be carried by particles traveling backward in time relative to us. Yet, the very fact that we can conceive of such a reality, that the mathematics allows for it, tells us that our own flow of time may not be a universal constant, but a local condition. The exploration of time's arrow inevitably leads us to the bizarre rules that govern the smallest scales of existence, where the very act of observation can alter reality itself. Quantum mechanics reveals a layer of reality far stranger than any mirror. Here, particles exist in a haze of probability, being in multiple places or states at once until a measurement forces them to choose. This bizarre world of superposition and entanglement might be the very thread that connects our universe to its hidden twin. The search for this link pushes us to the very edge of known physics, to hypothetical particles known as mirror fermions. These would be perfect shadow versions of the electrons and quarks that make up our world, obeying identical quantum rules but completely isolated from our electromagnetic force. They form their own mirror atoms and mirror chemistry, a parallel reality operating just beyond our perception. The most promising bridge between these two cosmic sectors could be the most elusive particle we know, the neutrino. These ghostly particles barely interact with normal matter, trillions passing through your body every second without a trace. This aloof nature makes them the perfect candidate for a cosmic ambassador. Theories propose a neutrino portal, a subtle mixing between ordinary neutrinos and their mirror counterparts. In this scenario, a neutrino produced in the heart of our Sun could, as it travels, momentarily transform into a mirror neutrino, effectively vanishing from our reality. It would step through a hidden door we cannot see. Experiments deep underground and in the Antarctic ice are hunting for this exact phenomenon. Detectors like MINOs carefully track beams of neutrinos sent over long distances, watching for any that inexplicably disappear. The Ice Cube Observatory, with its thousands of sensors buried in a cubic kilometer of clear ice, monitors for neutrinos from cosmic cataclysms, analyzing their flavors for any anomalies that suggest a fleeting journey into the mirror realm. This quantum connection profoundly blurs the line between separate universes. They may not be entirely isolated domains, but subtly entangled, their most fundamental components whispering to one another across a dimensional divide. The act of observing a neutrino here could, in some strange way, influence its mirror twin there, linking the fates of both worlds through the spooky, non-local handshake of quantum mechanics. This is no longer just a story of two separate realities, but of a single, deeply interconnected quantum cosmos. If the particles that form the bedrock of our existence can flicker in and out of a mirrored state, what does that say about the solidity of our own world? Our own consciousness may just be a single version of a cosmic story. If a mirror universe with inverted time and matter is real, could it also host conscious beings living lives that feel as immediate and real as our own? In their reality, a being might recall events from what we call the future with perfect clarity, while the past remains an anticipated surprise. Their entire experience of cause and effect would be reversed, yet from their perspective, it would be the only normal they have ever known. This is not a flaw in the hypothesis, but its most profound challenge to our understanding. It forces us to confront the anthropic principle, the observation that our universe happens to have the precise conditions necessary for life. We are here because the constants of nature allow it, but if a mirror cosmos exists with opposite physical laws, it could also be tuned for its own form of life, built from antimatter and thriving under conditions we would find lethal. The universe would not be fine-tuned for one type of existence, but for a duality of realities, each with its own valid claim to being real. This ontological duality raises unsettling questions about identity and free will. If every action here has a mirrored counterpart there, are our choices truly our own, or are they part of a balanced cosmic equation? Does moral responsibility extend across this divide, or is each universe an isolated ethical theater? Philosophers like Nick Bostrom have asked if we might be living in a simulation, but a mirror cosmos presents a different kind of duality, one made of physical law rather than computer code. It suggests that the foundations of existence might be fundamentally relational, that our reality is defined by its opposition to another. Engaging with these ideas does more than expand our scientific horizons. It connects the equations of physics to the deepest metaphysical questions about who we are and what reality actually means. By considering a cosmos where everything is flipped, we are forced to scrutinize the very assumptions that shape our daily lives, setting the stage to see how this profound idea has echoed through human culture for centuries. Long before physicists wrote equations for antimatter, storytellers were gazing into polished glass and seeing another world. Lewis Carroll's Alice stepped through her drawing room mirror into a kingdom where logic was inverted. Memory was unreliable, and the Red Queen declared a sentence first, then the verdict. This was more than fantasy. It was a profound exploration of a reality where every rule we take for granted is flipped. That same chilling inversion echoes in Star Trek's Mirror universe, where a simple transporter accident reveals an empire built on brutality and betrayal, a dark reflection of the Federation's ideals. These narratives are not just entertainment, they are cultural containers for our deepest anxieties about ourselves. What if we were someone else entirely? What if our best intentions had sinister counterparts? The ancient Greek myth of Narcissus warns of the peril in becoming captivated by your own reflection, a self-obsession that leads to destruction. Eastern philosophies formalized this duality into the elegant balance of yin and yang, opposing forces that are interconnected and essential to a complete whole. Darkness is not the absence of light, but its necessary partner. This human fascination with the double, the shadow self, found its way into the unsettling worlds of authors like Philip K. Dick, in his novel The Man in the High Castle, the Axis powers won World War II, and America is partitioned between Japan and Nazi Germany. The characters move through a history that is eerily similar to our own, yet horrifyingly distorted, a world where commonplace artifacts from our timeline become sacred, forbidden relics. This alternate history holds up a dark mirror to 20th century society, forcing readers to confront the fragility of their own reality. These cultural stories do more than just prefigure scientific ideas, they shape the very questions we are willing to ask. They prepare the public imagination to accept that the cosmos might be far stranger than it appears, that a mirror universe is not just a physicist's pipe dream, but a modern incarnation of an ancient archetype. The resonance of the hypothesis beyond academia lies in this deep cultural groundwork. We have been training for this idea for centuries through folklore and fiction, learning to see the world not as a singular, solid truth, but as one possibility among many. Science and storytelling are not opposing forces, they are two different languages describing the same profound mystery. One uses data and detectors, the other uses metaphor and myth, and together they enrich our understanding of what it means to exist in a cosmos that might be looking back at us from the other side of the glass. A modern television screen flickers with the same ancient fascination, portraying mirror universes not as abstract equations but as tangible worlds. Series like Stranger Things or Doctor Who transform the cosmic into the personal, framing alternate dimensions as places where characters confront twisted versions of themselves and their choices. The Marvel Cinematic Universe's sprawling multiverse is a prime example, presenting mirrored heroes whose divergent paths explore the profound weight of identity and the roads not taken. These stories are gripping because they tap into a fundamental human question: who would we be if one pivotal moment had gone differently? Yet for all their narrative power, how accurately do they reflect the underlying science? The truth is, they take significant creative liberties. Hollywood's mirror universes are often accessible through portals or technological gateways, a far cry from the gravitational isolation or quantum flickering proposed by physicists. They frequently conflate the idea of a parallel cosmos with time travel, creating a blended and scientifically messy concept. Astrophysicist Neil deGrasse Tyson and other science communicators regularly critique these inaccuracies, pointing out where entertainment diverges from established physics. But they also highlight an invaluable upside. These fictional depictions serve as a powerful gateway. They ignite curiosity in a generation of viewers who might never pick up a textbook on quantum mechanics. A child watching a hero navigate the upside down is introduced to the concept of a hidden reality, a seed that can grow into a lifelong passion for cosmology. This is the double-edged sword of popular science communication. On one hand, it makes profound ideas emotionally resonant and accessible. On the other, it can cement misconceptions, leading the public to imagine traversable wormholes between realities as a simple engineering problem. The power of these narratives lies not in their factual precision, but in their ability to frame scientific possibility as a human drama. By turning complex physics into stories about choice, destiny, and identity, they build a cultural bridge to concepts that might otherwise remain locked in academia. This widespread cultural absorption of the mirror universe idea, for all its simplifications, has primed the public imagination for a stunning possibility that scientists are not just writing stories, they are building machines to find it. Our search for a cosmic reflection now demands tools that can listen to the silent language of gravity itself. We are building machines that do not just see the universe, but feel its hidden dimensions. At the forefront of this hunt are gravitational wave observatories like LIGO and Virgo. These are not telescopes in any traditional sense. They are colossal, L-shaped instruments that use lasers to measure the infinitesimal stretching of spacetime. When two black holes spiral into each other in a distant galaxy, their colossal merger sends ripples across the cosmos, vibrations so subtle they change the length of the detector's arms by less than the width of a single proton. Now scientists are asking a revolutionary question. What if some of these ripples do not come from our universe at all? A mirror black hole composed of mirror matter would be completely invisible to our eyes. But its gravity is real. A collision in that other realm would create gravitational waves that wash through our own, leaving a faint, telltale wobble in the data. Future space-based observatories, like the planned LISA mission, will be sensitive enough to listen for these echoes from the very dawn of time, potentially capturing the primordial tremors from when the mirror universe first separated from our own. Alongside these grand cosmic listeners, particle accelerators are probing the void for hidden doorways. Inside the Large Hadron Collider, protons are smashed together at nearly the speed of light, recreating the conditions of the early universe. Physicists meticulously sift through the debris of these collisions, searching for something that should not be there. They hunt for exotic particles like the dark photon, a hypothetical carrier of a mirror force. If it exists, a dark photon would be a bridge, a particle that could, for a fleeting instant, interact with both our matter and mirror matter. Its discovery would be the first direct evidence of a hidden sector of reality. This search is complemented by a new generation of incredibly sensitive quantum sensors. These devices can detect the faintest gravitational tugs, so precise they could theoretically register the presence of a mirrored object drifting near Earth. The very presence of a mirror asteroid or a small mirror planet in our solar system would exert a minute gravitational pull, a ghostly fingerprint that these next-generation sensors are designed to capture. Every tool we build is a test of our imagination against the hard limits of reality. Our most powerful neutrino detectors, buried deep in ice and under mountains, monitor these ghostly particles for any sign that they are flickering in and out of our reality. When a neutrino seems to vanish without a trace, it might be temporarily stepping into the mirror sector. Each unexplained anomaly in the cosmic microwave background map, each strange particle decay that defies the standard model, and every gravitational wave signal with no visible source is a potential clue. These technological marvels represent humanity's most ambitious attempt to answer an ancient question. Are we alone in the cosmos, or is our existence part of a vast, balanced duality? Yet for all our ingenuity, the greatest obstacles to finding an answer are not just technological, but woven into the fundamental fabric of the universe itself. Even the most elegant theory must survive a brutal confrontation with reality. The search for a mirror universe is a hunt for whispers in a cosmic hurricane, where the very laws of physics seem designed to hide the evidence. The central obstacle is the profound weakness of the only bridge we suspect exists: gravity. If mirror matter interacts with our world solely through its gravitational pull, its signal is incredibly faint, easily lost in the background noise of our own universe's violent astrophysical processes. Think of trying to detect the gentle wake of a single ghost ship on an ocean churned by perpetual storms. This is the sensitivity our instruments must achieve. Our most powerful particle colliders face another daunting wall: the energy barrier. The Large Hadron Collider smashes protons together with unimaginable force, but the energy required to actually create a mirror particle, if it exists at all, might be far beyond what our current technology can muster. It is like trying to chip a piece off a diamond with a wooden hammer. We simply may not yet have the tools to knock on the door hard enough for anyone on the other side to hear. The clues we do find from cosmology are often frustratingly ambiguous. That strange alignment in the cosmic microwave background, the axis of evil, could be a fingerprint from a mirror universe collision, or it could just be a statistical fluke in the data, a cosmic mirage. Scientists must constantly guard against confirmation bias, the deeply human tendency to see a desired pattern in random noise. We so want the pieces to fit that we might accidentally force them together. This is where the principle of parsimony, often called Occam's razor, raises a stern philosophical objection. This principle advises that when faced with multiple explanations for a phenomenon, the simplest one is usually preferable. Why invent an entire parallel cosmos with all its inverted laws and particles, when more conventional physics might eventually explain dark matter or the matter-antimatter asymmetry? Perhaps dark matter is just a new, undiscovered particle within our own universe, not the ordinary matter of another. These challenges are not roadblocks to scientific progress, they are its very foundation. The rigor of this process, this constant back and forth between bold speculation and skeptical scrutiny, is what separates science from fiction. It forces theorists to sharpen their models and make more precise, testable predictions. By facing these limitations head-on, we do not abandon the quest, we simply acknowledge the immense difficulty of the task. This honest appraisal of the challenges prepares us for the ultimate question: what if the mirror universe is not the answer? What other breathtaking possibilities could explain the profound mysteries still written in the stars? A cosmic buffet of realities offers more than just a single mirrored dish. The mirror universe is a compelling idea, but it shares the theoretical stage with other grand visions of what lies beyond our observable horizon. Each one presents a unique solution to the puzzles of dark matter and our lopsided existence. The sprawling multiverse, for example, suggests not one opposite but an infinite ensemble of universes, each with its own randomly selected laws of physics. In this vast landscape, a mirror cosmos would be just one peculiar possibility among countless others, not a necessary twin. Our universe would be one where matter won by chance, while another might be dominated by antimatter, not because of a precise symmetry, but simply because the cosmic dice landed that way. This is a fundamentally different kind of multiplicity. Then there are the Brane worlds of string theory, which we touched upon earlier. These models propose that our entire universe is a three-dimensional membrane, or brane, existing within a higher dimensional space called the bulk. Other branes could float right alongside ours, mere millimeters away in an unseen dimension. While a mirror universe could be one such brane, other branes might host realities with completely different particle types and forces, not a perfect inversion of our own. They are neighbors, not reflections. How do we make sense of this entire menagerie of possibilities? Physicist Max Tegmark offers a helpful framework, categorizing multiverses into distinct levels. Our familiar, infinite observable universe is level 1. The level 2 multiverse emerges from eternal inflation, a never-ending process spawning bubble universes, each with potentially different physical constants. This is where a mirror universe born from a specific symmetric rupture would find its home. It is a structured part of a larger ensemble, not a random fluke. Comparing these ideas sharpens our understanding of the mirror hypothesis. It forces a critical question: is a perfect, mathematically precise opposition necessary, or is our mirror twin just one slightly off-kilter version in an infinite crowd? The mirror idea is defined by its elegant balance and specific predictions, like gravitational echoes and sterile neutrinos. The broader multiverse is more anarchic, explaining our fine-tuned constants not by design, but by the sheer statistical weight of infinite possibilities. Placing the mirror universe within this wider context does not diminish its appeal, it tests its resilience. It encourages us to think like a scientist, weighing which theory offers the most explanatory power for the clues we have. Does the specific nature of dark matter point to a mirrored sector, or does the sheer weirdness of quantum mechanics better support a vast multiverse? This comparative landscape, rich with competing ideas, directly fuels the next phase of our quest, guiding the telescopes and colliders of tomorrow toward the most promising targets in the hunt for reality's hidden layers. The next generation of telescopes will not just be looking for new stars, but for the ghostly architecture of another reality. Imagine a space mission designed not to study our universe, but to hunt for the absence of it. A dedicated mirror probe satellite could scan the heavens with instruments tuned to the faintest gravitational anomalies, seeking the precise wobble of a star that suggests an invisible mirror planet is orbiting it. This is not science fiction, it is the logical next step in a decades-long investigation. On Earth, our most precise timekeepers are joining the search. Atomic clocks, which measure the relentless tick of time using the vibration of atoms, are becoming so sensitive they could detect subtle variations in the fundamental constants of nature. If a mirror object passed near Earth, its gravitational field might minutely alter the flow of time in our local space, a distortion these clocks are now almost precise enough to register. It is like trying to hear the faintest whisper by making the entire room utterly silent. The James Webb Space Telescope, while not built for this specific purpose, is an unexpected ally. Its deep field observations, peering back to the earliest galaxies, could reveal large-scale structures that defy conventional models. A vast, empty region of space where galaxies seem to be pushed away by an unseen force, or a curious alignment of ancient light, could be the gravitational shadow of a mirror galaxy cluster. Meanwhile, the plans for the next generation of particle colliders are already on the drawing board. The Future Circular Collider, a proposed machine with a circumference over 50 miles long, would smash particles together with energies far surpassing the Large Hadron Collider. In the fiery debris of these collisions, physicists hope to see the first direct evidence of a mirror particle, a dark photon flickering into existence for a fraction of a second before vanishing back into the hidden sector. In laboratories, quantum computers are being tasked with a new mission, simulating the conditions of a mirror cosmos. By manipulating qubits to obey the inverted laws of a mirror universe, scientists can run virtual experiments, watching how mirror galaxies form and evolve. These digital universes provide a testing ground, allowing us to predict what specific fingerprints a mirror reality would leave in our own data. Experts in the field suggest that within the next few decades, the convergence of these technologies will bring us to a tipping point. Gravitational wave astronomy will mature, quantum sensors will reach unprecedented sensitivity, and colliders will probe deeper into the fabric of reality. We may finally gather enough evidence to decisively rule out entire classes of mirror models, or we might stumble upon a signal so clear it forces a rewrite of every physics textbook. This forward-looking perspective transforms the mirror universe from a static idea into a living, breathing scientific quest. It empowers you to watch the headlines, knowing that each new discovery from a telescope or a particle detector is another piece of the puzzle. The hunt for our cosmic reflection is accelerating, pushing the very limits of technology and imagination to answer one of existence's oldest questions. A confirmed mirror universe would not just add a new chapter to our physics textbooks, it would set the entire book on fire. The Standard Model, our most precise map of the particle world, would suddenly appear as a small, local ordinance governing just one half of a far grander reality. Every known particle, from the humble electron to the elusive Higgs boson, would have a hidden twin operating under a parallel set of mirror forces. This expansion would elegantly solve some of the most stubborn puzzles in physics. Take the hierarchy problem, the baffling question of why gravity is so unimaginably weaker than the other fundamental forces. The answer could be that gravity is not weak at all, but rather, it is the only force that leaks across the cosmic divide, diluting its strength as it stretches between our world and the mirror realm. This very idea provides a pathway to the holy grail of physics, a unified theory that seamlessly merges the quantum world with Einstein's general relativity. The immense energy of the vacuum, which drives the accelerating expansion of the universe we call dark energy, might find a natural explanation. It could be the subtle gravitational pressure exerted by the mirror universe's own expansion, a cosmic push from the other side of reality. Visionaries like Stephen Hawking explored how quantum mechanics allows for multiple histories, and a mirror cosmos would be the ultimate expression of that, a separate but equally real timeline with its own physical laws. The theoretical frameworks for this already exist, built on new mirror-gauge symmetries and warped geometries of space-time, but the implications reach far beyond pure theory. If we could ever learn to interact with this hidden sector, the technological possibilities would be staggering. We might tap into mirror energy sources or develop propulsion systems that manipulate the gravitational link between the two worlds. This profound shift in understanding reminds us that the most audacious ideas are the engines of scientific progress, forcing us to look beyond our local reality and ask what other cosmic secrets remain hidden in plain sight. Our cosmos is not a static stage, but a story still being written, and the mirror universe could be a character we have yet to properly introduce. This hypothesis weaves itself directly into the grand narrative of cosmology, from the first flash of the Big Bang to the ultimate fate of everything. It suggests that the entire evolutionary playbook of the universe might have been run twice, once for matter and once for its perfect opposite. While our universe forged its first atoms in the furnace of Big Bang nucleosynthesis, a mirror cosmos would have done the same, but with mirror particles fusing into mirror helium and mirror lithium. As gravity pulled our matter into galaxies and stars, it would have pulled mirror matter into mirror galaxies and mirror stars, creating a parallel cosmic web we cannot see. This elegant duplication offers a fresh perspective on some of cosmology's most stubborn numbers. Take the Hubble constant, the rate at which the universe is expanding. Different methods for measuring it yield slightly different results, a discrepancy known as the Hubble tension. Could the presence of a mirror universe be the reason? If mirror radiation and mirror particles contribute to the overall energy density of the cosmos, they would subtly alter the expansion history, potentially reconciling these conflicting measurements. This hidden component would act like an invisible hand, gently tweaking the rate of cosmic growth. The influence might even be detectable in the effective number of neutrino species, a parameter deduced from the cosmic microwave background. Extra sterile mirror neutrinos could blend into this count, their presence inferred only by the subtle shadow they cast on the ancient light. By framing the mirror universe not as an isolated idea, but as an integral piece of the cosmological puzzle, we see its true power. It connects the mystery of dark matter to the saga of cosmic structure formation, and the riddle of the Hubble tension to the first moments of time. This integrated view transforms our universe from a solo performance into a potential cosmic duet, setting the stage to examine the strange soloists in this symphony, the mirror stars and black holes that might populate the darkness. A star you cannot see could be warming a world you will never visit. This is the reality of a mirror star, a sun composed entirely of antimatter. Its heart would burn with the same nuclear fusion as our own sun, but with all the particles reversed. Positrons would collide with antiprotons, releasing a torrent of energy in the form of mirror photons. To any instrument that detects ordinary light, this star would be utterly dark, a perfect void in space. Yet its gravity would be real and measurable, warping the paths of visible stars and bending the light from galaxies behind it. The life cycle of such a star would mirror our own in a grand, invisible dance. A vast cloud of mirror gas and dust would collapse under its own gravity, igniting into a mirror main sequence star that burns for billions of years. When its mirror fuel is exhausted, it could explode in a cataclysmic mirror supernova, scattering newly forged mirror elements across its galaxy. The remnant could be a mirror neutron star, an impossibly dense ball of mirror neutrons, or even collapse into a mirror black hole whose gravity is indistinguishable from our own. Around these dark suns, entire planetary systems could form. Imagine a mirror Earth with continents of mirror rock and deep oceans of anti-water. In this anti-water, hydrogen atoms would have a positive charge and oxygen a negative one, yet the chemistry could be similar enough to form complex molecules. The possibility of mirror life is not so far-fetched. Ecosystems could thrive there, built on a foundation of opposite chirality, where the fundamental handedness of biological molecules is flipped. A mirror amino acid would be useless to our biology and ours to theirs, but it could form the basis for its own intricate, living world. The astonishing thing is, we may have already seen hints of these shadow worlds. Gravitational microlensing surveys, which watch for stars that temporarily brighten when an unseen object's gravity focuses their light, have recorded countless events. Among them could be the subtle, telltale flare caused by an invisible mirror planet drifting in front of a distant star. This means our telescopes may have already recorded the ghostly passage of another Earth, a world built from a substance we can never touch, orbiting a sun we can never see. The cosmos suddenly feels far more crowded, filled with structures and lives that are forever just beyond our perception, compelling us to ask what it would mean to finally make contact. A mirror organism would find our world utterly poisonous. The very molecules that build our bodies, the amino acids, are almost exclusively left-handed, a specific twist in their structure known as chirality. This handedness is as fundamental to life as a key is to a lock. Our enzymes, the machines that drive our metabolism, are shaped to fit only left-handed amino acids. A right-handed version of the same molecule would be biologically inert, a key that simply will not turn. In a mirror universe built on opposite symmetries, the logic would be perfectly flipped. The amino acids forming the foundation of mirror biology would be uniformly right-handed. A protein from our world would be as useless to a mirror cell as a left-handed glove is to a right hand. This is not a minor difference, it is a fundamental barrier that would make the biochemistry of the two realms completely incompatible. For life to emerge in such an environment, it would need a consistent foundation. A mirror planet would require liquid solvents, most likely mirror water, where the electrical polarity of every molecule is reversed. It would need a stable energy source, the consistent warmth of a mirror star driving mirror photosynthesis in mirror plants. The planet itself would have to orbit within the habitable zone of its dark sun, a region where temperatures allow mirror water to flow as a liquid. While this is all highly speculative, physicists and astrobiologists like Paul Davies suggest that the underlying principles of life might be universal. Life, in its essence, is a system that processes information, maintains complexity, and resists decay. These functions could, in theory, be realized under different physical laws, using a different set of molecular building blocks. A mirror being would not experience its own time as running backward, any more than we feel our blood flow. Its consciousness would be adapted to its own arrow of time, its memories and anticipations aligned with a universe where effects unfold from causes in the opposite sequence. The possibility of mirror life forces a profound expansion of our perspective. It challenges our Earth-centric view of biology and suggests that the phenomenon of life could be a truly cosmic imperative, a spark that ignites wherever the conditions for complexity exist, even in a reality that is the perfect inverse of our own. If we were to one day detect the gravitational signature of a mirror Earth, we would be faced with an unprecedented ethical dilemma. A confirmed mirror Earth would present humanity with an ethical dilemma of cosmic proportions. Our first instinct might be to communicate, to reach out and confirm we are not alone in the grand duality. But what if our very attempt at contact is an act of violence? An experiment in our universe, perhaps a high-energy particle collision, could theoretically create a ripple affecting their reality. A gravitational wave detector here might be a source of a deafening sonic boom there. If our actions inadvertently harm a mirror civilization, have we committed a crime against a universe or simply against ourselves in another form? This forces us to confront the principles of cosmic ethics, a philosophical framework that argues for moral consideration to be extended to all conscious beings, irrespective of their biological makeup or cosmic address. Their sentience, their capacity for experience, is what grants them moral standing. The classic science fiction concept of a prime directive, a strict policy of non-interference with developing civilizations, becomes exponentially more critical when applied to a mirror reality. The risks of misunderstanding are astronomical. A message of peace encoded in our matter could be interpreted as a declaration of war in their antimatter-based logic. Experts in the emerging field of astrophysics are deeply divided. One school of thought advocates for cautious, passive listening, studying their universe for signs of technology or art without ever transmitting a signal. The other argues that our mere existence, our gravitational presence, is already a form of contact, and that we have a duty to announce ourselves and seek a shared understanding. This is not a remote philosophical exercise. It underscores a profound shift in humanity's role. We are no longer just inhabitants of a single planet, but potential neighbors in a multiverse. Our scientific curiosity must be tempered with a deep sense of cosmic stewardship. Every new experiment probing the fabric of reality must now be considered for its potential cross-dimensional consequences. By grappling with these questions, we bridge the gap between cold equations and warm morality, realizing that the ultimate discovery may not be a new universe, but a new responsibility for our own. A mirror cosmos does more than challenge physicists. It transforms how we teach science to everyone. In a bustling classroom, a teacher holds up two seemingly identical gloves. One fits a student's left hand, the other their right. This simple, tangible object becomes a gateway to discussing parity violation, that moment when the universe revealed its hidden left-handed preference. The mirror universe hypothesis provides a narrative scaffold, a story that makes abstract ideas like antimatter and symmetry breaking feel immediate and real. Students are not just memorizing facts, they are exploring a cosmic detective story, asking what a perfect opposite of our world would be like, and, in the process, internalizing the fundamental laws that govern our own. This educational power extends far beyond school walls. Major documentaries and planetarium shows use stunning visualizations to portray two overlapping realities, helping audiences literally see the invisible forces of dark matter as the gravitational pull of a hidden twin. Online, channels like Cosmological employ vibrant animations to illustrate how a mirror neutrino might flicker between dimensions, turning complex particle physics into a clear and compelling visual journey. These resources demystify cosmology, replacing intimidation with a sense of shared discovery and wonder. They foster a crucial form of critical thinking, training minds to question assumptions about reality itself. Yet this power comes with a responsibility for precision. The line between a helpful analogy and a misleading oversimplification is delicate. An educator might brilliantly use the mirror concept to explain why matter survived the Big Bang, but they must also clarify that we cannot simply step through a portal into this other realm. The goal is to balance the spark of imagination with the rigor of scientific accuracy, ensuring that wonder is built on a foundation of truth. This widespread dissemination does more than entertain. It builds scientific literacy on a societal scale. By engaging with these grand, speculative ideas, the public becomes a partner in the scientific process, better equipped to understand the significance of a new gravitational wave signal or an anomalous particle detection. The mirror universe becomes a unifying narrative, a story that connects the dots between particle physics, cosmology, and the philosophy of science, showing how disparate fields can converge to tackle the deepest mysteries of existence. A mirror universe is not just a topic for physicists, it is a catalyst for conversations that span the entire landscape of human knowledge. In computer science, programmers run sprawling simulations on supercomputers, crafting digital universes where the fundamental laws are flipped, watching as mirror galaxies form under the subtle tug of reversed gravity. These are not mere video games, they are virtual laboratories, testing how mirror matter would clump and evolve across billions of virtual years. Artists, in turn, absorb these digital explorations, translating them into immersive installations where visitors can walk through spaces where light and shadow are inverted, and sound seems to originate from its own echo. These creations make the abstract tangible, allowing us to feel, for a moment, the disorienting wonder of a truly opposite reality. The dialogue extends into biology, where cosmologists collaborate with astrobiologists to map the prerequisites for mirror life. They ask what a stable mirror DNA molecule might look like, with its chirality perfectly flipped, and what solvents on a mirror Earth could cradle such exotic biochemistry. This pushes the search for life beyond our own cosmic neighborhood, suggesting that biosignatures could exist in forms we have not even begun to imagine. Philosophers grapple with the epistemic weight of these claims, questioning how we could ever truly know a reality that is, by its very nature, designed to be undetectable. They explore whether a mirror cosmos is a scientific proposition or a metaphysical necessity, a modern incarnation of an age-old puzzle about the nature of existence itself. Even the mathematics of symmetry, expressed through the elegant structures of group theory, provides the fundamental language that allows physicists to draft the blueprints for these mirrored realms. And in a poignant parallel, the study of mirror neurons in our own brains, the cells that fire both when we act and when we see another act, offers a powerful biological metaphor for a cosmos that might reflect our own. This cross-pollination of ideas does more than just generate new papers. It breaks down the walls between disciplines. It proves that the biggest questions cannot be contained within a single field. They demand a holistic perspective where a physicist's equation can inspire a painter's vision, and a philosopher's doubt can sharpen a biologist's hypothesis. This collaborative spirit, ignited by a single cosmic idea, reminds us that the pursuit of knowledge is a unified human endeavor, forever pushing against the boundaries of the known. This grand cosmic duality is not just a theory for physicists, it is a mirror held up to our own lives. Pause for a moment and think, how does the possibility of a perfect opposite cosmos change your perspective on the world you see every day? Does it make you value the sheer, unlikely uniqueness of our own universe, with its stable stars and forward-flowing time? Or does it make you question the very nature of your own choices? If every decision here is balanced by an inverted counterpart there, what does that say about free will? We want to hear your thoughts, so share them in the comments below. What would you do if you somehow encountered your mirror self, a person who lived your life in perfect reverse? If time flowed backward for you, what single moment would you choose to relive, not to change it, but to experience it anew from its end to its beginning? And how would our entire society change if we received undeniable proof that a mirror Earth existed, with its own history and its own people? Would it spark a new age of cosmic humility, or a desperate race to bridge the unbridgeable gap? This is more than a thought experiment. It is a way to connect the vast, impersonal scales of cosmology to the intimate scale of human experience. By reflecting on these questions, you transform from a passive viewer into an active participant in this great mystery. Your personal reflections make the science memorable, turning abstract equations into stories about our own lives and choices. This shared curiosity builds a community, right here, all wondering together about the deepest nature of reality. The idea of an evil twin universe makes for great television, but it bears little resemblance to the scientific hypothesis. In a true mirror cosmos, the inhabitants would not be malevolent versions of ourselves. They would simply be the product of their own physical laws. Good and evil are human concepts, not properties dictated by the charge of an electron or the direction of time. The real theory strips away this moral baggage to focus on a stark physical inversion. Another widespread myth is the assumption that matter and mirror matter would instantly annihilate each other on contact. This is not necessarily true. If the mirror universe operates with its own separate set of forces, its particles may have no way to interact with ours electromagnetically or through the nuclear forces. They could pass through each other like ghosts, completely unaware, their only connection the faintest whisper of gravity. This fundamental isolation also shatters the sci-fi trope of easy travel. You could not simply step through a looking-glass portal. The two realities could be separated by a higher spatial dimension, forever out of reach, or they might only interact through quantum particles that flicker between states. Leading physicists constantly caution against the sensationalism that often surrounds this idea. The mirror universe is a rigorous theoretical framework, a set of mathematical possibilities that answer specific cosmic puzzles. It is not proven fact. This distinction is crucial for scientific integrity. Embracing these clarifications does not make the idea less exciting, it makes it more profound. By moving beyond the myths, we engage with the hypothesis as it truly is, a daring but disciplined attempt to understand why our universe is the way it is. This clear-eyed perspective prepares us to weigh its true significance for our place in the cosmos. Symmetry is the silent architecture of reality, visible in the six-fold perfection of a snowflake and the vast spiral arms of a galaxy. Nature seems to favor this balance, but its true power is revealed in the moments it breaks. The mirror universe hypothesis elevates this principle to its ultimate expression, proposing that perfect symmetry might govern the entirety of existence, even if we only perceive its fractured reflection. The very laws that shape our world are built upon fundamental symmetries, like Lorentz invariance, which ensures the laws of physics are the same for all observers moving at constant speed, and gauge symmetries, which underlie the forces that bind atoms together. These are the deep, invisible patterns that make reality coherent. Yet, it is the breaking of a specific symmetry, the slight preference for matter over antimatter, that allowed our universe to come into being at all. This flaw is not a mistake, but the source of all diversity, the crack through which complexity could emerge. Mirror models offer a breathtaking resolution to this paradox. They suggest our local imbalance is merely one half of a global, perfect symmetry. The profound CPT theorem stands as a pillar of this idea. It states that if you reverse the charge of every particle, flip its parity as if in a mirror, and run time backward, the laws of physics must remain unchanged. Our universe obeys this rule perfectly. A mirror cosmos would be the physical embodiment of this ultimate transformation, a realm where the CPT operation has been applied to everything. In this grand view, the two universes together form a single, invariant whole. Our lopsided, matter-filled existence is balanced by its antimatter, time-reversed twin. The elegance of this proposition connects the hypothesis to the deepest principles of physics, revealing a cosmos that strives for harmony even in its apparent discord. By understanding symmetry not as a static pattern but as a dynamic, sometimes hidden force, we see why the mirror idea is so compelling to scientists. It transforms a puzzling asymmetry into a signature of a deeper, more beautiful order, preparing us to consider the ultimate implications of this cosmic reflection. Our journey through the looking glass brings us to a final, humbling reflection. We have traced the contours of a perfect opposite cosmos, from the left-handed bias of subatomic particles to the gravitational whispers of dark matter halos. This grand hypothesis does far more than propose a hidden twin. It holds a mirror to the very process of science itself. It shows us how a single, elegant idea can weave together the deepest puzzles of existence, from the missing antimatter to the nature of time's arrow, transforming our flaws into signatures of a vaster, hidden symmetry. While the definitive proof remains just beyond our grasp, the pursuit has already reshaped our understanding, pushing the limits of technology and forcing us to confront profound philosophical and ethical questions about our place in the cosmos. The universe is under no obligation to conform to our imagination, yet the mere possibility of a mirror reality expands our horizons and fuels our innate drive to explore. As Carl Sagan so beautifully reminded us, somewhere, something incredible is waiting to be known. That incredible something might be a universe of antimatter stars and inverted time, or it might be an even more breathtaking truth we have yet to conceive. We thank you for joining this exploration. Share your own thoughts and reflections in the comments below, and if your curiosity is sparked, subscribe for more journeys to the edge of understanding. Keep looking up and never stop questioning the reflection you see in the cosmic